Good morning, or whatever it happens to be, wherever you are. Welcome to Humke's study in abstentia. Today, I'd like to talk a little bit about the first part of the next chapter, determinants. And maybe the first thing is, what the heck does a determinant determine? And this is for linear transformations. So some linear transformations are congruences. These are technically called isometries. And these maintain all angles and all distances. So if you have two objects that are congruent, like two triangles that are congruent, and you operate on them by some linear transformation, it may change them, but they will remain congruent, and they will look like what they did before. So rotation, for example, is an isometry. But not all linear transformations are isometries, far from it. Some of them are similarities. So if two objects are similar, that is, their sides are, all their dimensions are proportional, then the images will also be similar and have the same proportions. But not all linear transformations are similarities either. But one property that linear transformations have that's very nice is that if, for example, we take a square, say 3 by 3 square, so it has area 9, the linear transformation might take it into an object that doesn't have area 9. Maybe it's got area 27. Then what happens is that if you take any object over here, maybe the area is 7, and you look at the image of that area over here, it can change a lot, but the area is going to be 21. And the determinant in this case of the linear transformation is that proportion 3. All areas here get mapped into exactly 3 times the area that they were before. And this determinant there then is determining this ratio of areas, or if it's 3-dimensional volumes, or if it's 4-dimensional hypervolumes. So there are some things to know about determinants, and this is one of them. Maybe the important one is what it actually does. The second thing is how to compute. These. Mathematica does it very well with DET, capital DET will give you the determinant of a matrix, and these only work for square matrices because we're mapping a space into itself. But I'd like to show you how to compute these by hand, and I'll do it by example. So we'll take a 3 by 3, 3, 1, 2, 2 minus 1, 4, 1, 1, I don't know, minus 2. Make it up as we go. The first thing to do is to choose any row or column. It doesn't matter. You can choose a row or you can choose a column. And so maybe we'll take the third row here. And we're going to what's called expand about this using row 3. And how does this expansion go? Down here, this is the A third row first column term, the A third row second column term, and the A third row third column term. Each of these terms comes with a corresponding matrix, M31. And to get M31, you look at the matrix consisting of everything that's not in this guy's row or column. And if you look at everything that's not in its column, everything that's not in its row, you get this matrix right here. And this is called a minor, 1, 2, minus 1, 4. And each one of these terms has its own minor. So we'll color, I use this, let's color code with green. So the minor of A32, the minor of A32, which is hardly visible in green, I guess. Yellow was good. We'll try blue, M32. So everything that's not in its row or column will consist of 3, 2, 2, 4. And the third one, which may be orange, A33, gives the minor M33. M33, 3, 1, 2, minus 1. Everything that's not in its row and column. So there we go. Each of these has a minor. And what we're going to do is expand this using row 3 and determinants of these minors. A 2 by 2 determinant, I'll show you how to do that. And once you can do a 2 by 2, that will allow you to find determinants of these minors. And then we'll use those together with these values to get the determinant of this. So the determinant of this will be A31, which is the number 1, times the determinant. The determinant can be DET, but it can also be bars, which makes it easier to write. 1, 2, minus 1, 4. And then 1 times the determinant of its minor, 3, 2, 2, 4. And then minus 2 times the determinant of its minor, 3, 1, 2, minus 1. Well, there's one thing in addition that I didn't tell you yet, and that is that these come with signs. So this sign here will either be plus or minus, the sign here will either be plus or minus, the sign here will either be plus or minus. And those are always determined beginning at the upper left, which is plus, plus, minus, plus, minus, plus. And those signs are in addition to the signs of the numbers that may appear here. So the first one is plus. This one has a minus, so that'll make this part minus. This one is plus, and that means you use the minus 2. If this would have been a minus, then we would have had a minus 2, or plus. It would have changed that sign, just like the minus up here changed that sign. So this is the expansion so far. And now I have to tell you how to find each of these determinants. And I'm going to erase the minors here, and we'll find those one at a time. So if we take the determinant of the minor, this is called the cofactor, C31. So that's the determinant of 1, 2, minus 1, 4. And you take this for a 2 by 2. That direction is a plus, minus this direction, plus, minus. So 1 times 4 is 4, minus a minus 1 times 2. So 4 minus a minus 2 is 6. So this number here is 6. This determinant is 6. So this first part becomes 1 times 6 minus, and then this determinant, 12 minus 4 is 8. And it's negative because of this sign on the cofactor. Doesn't change the sign of the term in the matrix. It's only used when determining these cofactors. And then minus 2 times minus 3 minus 2 is minus 5. 6 minus 8 minus 2 plus 10, 8. So this determinant is 8, meaning each area in the plane, this will be 3 dimensions, so each volume in the plane will be multiplied by 8 in the image. So this is very expansive. Every volume gets expanded. And let me just be clear here that the cofactor of 3, 2 does include this sign. So it would be minus the determinant 3, 2, 2, 4. All right, so this is how to compute. There are some simple kind of shortcut methods of doing it, but I would like you to learn this cofactor expansion, because the cofactor expansion works in any dimension, and the shortcuts sort of don't work in every dimension, or they change fairly radically in how you do them. One thing, the third thing I thought I'd show you is, because this can help in computations, is how these are affected by the elementary row ops. So how do the elementary row operations change things? So let's do this with a matrix. We know the determinant of 2, 3, 1, 4. So the determinant of this is 6 minus 4, or 2. So let's do an elementary row operation. Let's multiply 3 times row 1. 3 times row 1. So that gets me the matrix 6, 3, 4, 3. And its determinant will be 18 minus 12, or 6. This determinant was 2. So multiplying a row by a number will multiply the determinant by that same number. So if this is m, and this is m prime, the determinant of m times 3 is the determinant of m prime. Multiply a row by a number, and it will change the determinant by that same factor of 3. Another one is to interchange rows. So I forget what we had. Let's do 3, 4 here this time. So let's interchange row 1 and row 2. See what happens. 2, 1, 3, 4, 2, 1. So this determinant is 8, minus 3 is 5. This determinant is 3 minus 8, or minus 5. So this change of rows, the determinant of m and the determinant of m prime differed by a minus. Now, this doesn't always happen, but it happens with exchanging rows that are next to each other. If you exchange adjacent rows, it changes the sign. But if you had a third row and you exchanged with the first one, the sign wouldn't change. And you could think about that as first exchanging the the second and third, and then exchanging the second and first. So it takes two operations to move a third row to a first row. So the sign would change twice, meaning it wouldn't change at all. But adjacent rows introduce a negative sign with a determinant when you exchange them. The third one is pretty enlightening, actually. And that is that if you take a matrix here and let's take -1 times row 1 and add to row 2. -1 times row 1, add to row 2. So the first row stays the same, 2, 4. Minus this plus this is 0. Minus this plus this is 1. What do these kind of operations, how do they change the determinant? This determinant is 10 minus 8 is 2. This determinant is 2 minus 0 is 2. No change. So the determinant of M under these circumstances, under all of these, this type of elementary operation, elementary row operation, this operation does not change the determinant. So in particular, you can tell that if two rows of a matrix are the same, this determinant is going to be 0, because if you subtract those rows, you get a row of all zeros, and if you expand by a row of all zeros, you get 0. Or if two rows are just linearly, if your rows are linearly dependent, that means that one of them can be zeroed out. And as soon as one of them can be zeroed out by taking linear combinations of the others, determinant 0. So if your rows are linearly dependent, then this tells you that the determinant is going to end up to be 0. If they're independent, we already know that it doesn't end up to be 0. So this is what I'd like you to know about determinants, and I think I put up a homework assignment about them. And have a look. Adam will be there to kind of monitor things, and we'll see if we can get breakout rooms as you wish. If you have additional information, please send me soon, because Wednesday's coming up and I'm going to be gone. But I'll see you Friday. Looking forward to it. See you then. Bye.